Okay, we're now ready to start a new chapter of Math 5, the final chapter, which is about linear algebra. So let's begin that by reviewing what we did in the previous chapter, which is we proved a bunch of results about matrices and vectors. Now, mostly when we thought about the entries of those matrices, we thought about the entries as being real numbers or complex numbers. And actually it didn't make any difference to what we proved whether the matrices had real entries or complex entries. Everything we proved was still true. There are plenty of other kinds of numbers available to us. For example, integers, rational numbers, natural numbers. And it's natural to ask what kind of numbers the entries of our matrices and vectors have to be if we want all the results from the previous section to still be true. For example, we proved a result which said you can put any matrix into row-reduced echelon form by doing row operations. And that wouldn't be true anymore if you only allowed integers as the elements of your matrices. So one of the conditions of row-reduced echelon form is all the leading entries have to be 1. And in order to make that true, you would need to multiply by things like a half or a third and so on. And those things are not integers, which means we can't prove the row-reduced echelon form theorem if we only allow integers. So the answer to the question, what kind of numbers do you need for everything to be true, is everything is fine so long as the matrix entries come from what is called a field. Now, roughly speaking, a field is a collection of numbers where you can add them, you can multiply them, and you can divide by any non-zero number. So typical examples of fields would be the real numbers and the complex numbers, or even the rational numbers. But the integers are not a field because you can't divide an integer by an integer and get another integer answer. Like 1 divided by 2 or 2 divided by 7 are not integers. If you want to know the exact rules for what is and what isn't a field, you can look at the links in the lecture notes for this section, section 4.1. The basic idea, which is that a field is somewhere where you can add, multiply, and divide, is enough for what we're going to do. You don't need to know anything about the intricate details of the field axioms. What we're going to do, though, in these next couple of videos is to look at a family of interesting examples of fields which we've not used yet and which are very different to the fields which we've used so far. And those are the finite fields of prime order. So let's describe what the finite fields of prime order look like. You start off by choosing a prime number p, like 2 or 3 or 5 or 7 or 11 or whatever. And we're going to describe a field which has size p, so has only p different elements. It's going to be called the finite field of order p, and it will be written using this symbol here. So this bold F, this special bold F with a subscript p. So we might have F2 or F3 or F5 or F7 or whatever. Now, the elements of Fp can be thought of as ordinary integers, but we're going to change the definition of equality so that every element is equal to one of 0, 1, 2, 3, 4 up to p minus 1. And of course, there are p things there, so that's why it's called order p. The way we do this is that we regard every integer multiple of p as being equal to 0, so that x is equal to y. If x and y are two integers, we're going to write x equal to y in Fp if and only if the difference between x and y is a multiple of p. So I'll show you an example of this in a moment. But a field is supposed to have some operations. You're supposed to be able to add and multiply and even divide. And addition and multiplication are exactly the same as the addition and multiplication on ordinary integers, with this change that two things are going to be equal, two integers are going to be regarded as equal if and only if they differ by a multiple of p. Another way of putting that being to say that x is equal to y if and only if x minus y, the difference, is a multiple of this number p. So let's see what this looks like in practice. Let's look, for example, what happens in the finite field f5 of order 5. Well, then here we would have 3, and that's going to be minus 3, for example. That will be equal to 2, because the difference between minus 3 and 2 is a multiple of 5. It's 1 times 5, and that will be equal to 7, because the difference between 2 and 7 is a multiple of 5. It would also be equal to 17, because the difference between 7 and 17, or 2 and 17, or minus 3 and 17 is a multiple of 5. So that's how equality would work in F5. We can also do some arithmetic. So for example, 2 times 3 will be equal to 6. 2 times 3 is 6. But in F5, this is also equal to 1, because the difference between 6 and 1 is a multiple of 5. And if you had 2 plus 3, well, that will be equal to 5. And 5 is equal to 0 in F5, because 0 and 5 differ by a multiple of 5. Okay, let's try a different finite field. Let's look at F7. So in F7, let's do some more arithmetic. 2 plus 6 is equal to 8. And in F7, that's the same as 1, because 7 and 8 differ, because 1 and 8 differ by a multiple of 7. And let's do some harder arithmetic. 6 times 6, that is 36. And that is equal to 1, because the difference between 1 and 36 is a multiple of 7, right? The difference is 35, and that's 5 times 7. But equally, you could think of this multiplication we've just done as another way. In another way, 6 will be equal to minus 1, because 6 minus 1 is a multiple of 7. So if we wanted to work out 6 times 6 a different way, we could say that 6 times 6 was the same as minus 1 times minus 1. And of course, minus 1 times minus 1 is 1. And you'll be relieved to see we got the same answer both different ways we worked out 6 times 6. Okay, so that's how arithmetic works in these finite fields of prime order. If you've ever heard of modular arithmetic or modulo arithmetic, or looked at congruence modulo something, it's exactly the same thing that's happening here. If you've not, don't worry, it doesn't matter. So one thing I said about the definition of a field was you should be able to add and multiply, and okay, we've done some additions and multiplications. But what about dividing? You're supposed to also be able to divide by any non-zero number. So for example, what is 1/2 in the finite field of order 7? What would this be equal to? Well, that is something where when you multiply by 2, you should get the answer 1 again, right? If you multiply half by 2, you should get the answer 1. And if we just try out a few multiplications, what you'll find is that 2 times 4, well, that is equal to 8. And in the field with 7 elements, in F7, 8 is equal to 1. So 2 times 4 is equal to 1, and therefore 1 over 2 is equal to 4. Okay, remember, in the finite field Fp, every element must be one of 0, 1, 2, 3, up to p minus 1. So if we have this element 1 divided by 2, the multiplicative inverse of 2, that's got to be one of the numbers 0, 1, 2, 3, 4, 5, 6. And in fact, in this case, it turns out to be equal to 4. Okay, so let's just do a little more work on examples of finite fields to make sure we understand what's going on here. We're going to look at addition and multiplication tables. So you can summarize the whole of the arithmetic in a finite field by drawing up a table for each operation. And because there are only finitely many elements in these finite fields, we can draw up the complete table, which tells you all of the additions and multiplications. So we're going to do the table for F3, the finite field of order 3, whose elements are all equal to one of 0 or 1 or 2. So I can draw my table with just rows and columns labelled by 0 and 1 and 2, and in row I and column j we can put I plus j, or I times j. So let's do these tables for F3. So here we have the addition table on the left here. 0 plus 0 is 0, 0 plus 1 is 1, 0 plus 2 is 2. Okay, that was easy. And the first column will be easy as well, because I've got 1 plus 0, which is 1, and 2 plus 0, which is 2. So that's nice and easy. And then let's complete the second row. I'd have 1 plus 1 is 2, just here. And 1 plus 2 is 3 in the next entry. Now, there's nothing wrong with writing a 3 here, but usually we stick to only having the numbers 0, 1, 2 up to p minus 1 in the table. So instead of putting 3 there, I'm going to put a 0 there, because 3 is equal to 0 in the finite field F3. So let's record what we did. 1 plus 2 is equal to 3 is equal to 0 in F3. Okay, last row, 2 plus 1 is 3, which, as we've decided, is 0, and 2 plus 2 is 4, and 4 is equal to 1 because 4 and 1 differ by a multiple of 3. So I can put a 1 down here. Okay, let's do some multiplication. The multiplication table is even simpler because half of the time we're multiplying by 0. And of course, multiplying by 0 is always going to give us 0. And multiplying by 1 is just as easy. 1 times 1 is 1. 1 times 2 is 2. 2 times 1 is 2. So the only interesting one is what is 2 times 2? And of course, that is 4. And in the finite field F3, 4 is equal to 1 because 4 and 1 differ by a multiple of 3. So I can put a 1 here in my multiplication table. So you can find the addition and multiplication tables for F5 in the lecture notes for this section. If you've not done this stuff before, if you've not come across these finite fields or this modular arithmetic, I'd suggest trying to work out the addition and multiplication tables for F5 yourself and then checking your answers with the tables in the notes. So before we move on, I'm going to return to this question about division because, as I said before, in a field, as well as being able to add and multiply, you're supposed to be able to divide by any non-zero element. Now for F3, if we want to be able to divide by things, we can just look at the multiplication table. So for example, if we wanted to know what 1 over 1 was, well, of course, 1 over 1 is 1, because if you multiply 1 by 1, you get 1. And similarly, we know that 2 times 2 is equal to 1 in F3, so 1 divided by 2 will be equal to 2. And then we've now worked out all of the possible divisions. We've done 1 over 1 and 1 over 2, so we know how to divide by all of our non-zero elements. But what about for bigger primes? I mean, we tried this in F7, and if you wanted to work out 1 over 3 in F7, you could just try all the possibilities. It's not too many to try. But what about F17 or F some enormous prime number? How might we work out multiplicative inverses, so 1 over something in a larger field? That's what we're going to see in our next video.